Hi everybody, my name's Chris Collison, and today we're going to talk about the lab on chemical kinetics and a particular experiment where we're going to react some potassium permanganate with some oxalic acid. Now, potassium permanganate has a purple color, and that purple color is going to disappear as the reaction moves forward. And we're going to time how long it takes for that color change to disappear, and we're going to tie it back to some standard ideas in chemical kinetics. So this current video will give you some specifics about the experiment that we're going to run, and then you can step into the lab and follow it through. So thanks for your attention, and I hope you enjoy. So the topic of the class is the kinetics of reactions experiment. So what's happening in this particular experiment? Well, as I mentioned in my introduction, we're starting with this potassium permanganate solution, which is a purple color. And we're going to add this potassium permanganate solution to a mixture of oxalic acid, which is colorless. And we're going to, that oxalic acid, by the way, is also diluted down with some water. And what's going to happen over the course of time is the reaction is going to proceed, and we're going to lose this purple color, and the products will give us a yellowish or hopefully even colorless solution. And at that point, we'll know that the potassium permanganate has been used up, and we can measure the change in concentration, therefore, in the particular reaction. It's important to recognize how to write a rate equation, and so the rate equation is expressed down here, and there are three parts to this that are important. We have the orders of reaction, the X and Y here that are described in the background video, and also the rate constant in here. And the objective is to determine X, Y, and K in this particular part of the experiment. So what's the experimental plan? Well, here's a table that describes three different experimental sets, and we're going to do each one of these experimental sets 5 times. So basically, why are we doing it 5 times? There's going to be a significant amount of inaccuracy, and I'm not going to tell you where that comes from, but I want you to think about where that error comes from as you're going through this particular experiment. So you're going to do each experimental set 5 times. And you'll be able to measure an average and standard deviation there. Let's look for a second at the first experimental sets. We start in each case with 1 milliliter of this KMnO4. And what we're doing here is we're doubling the concentration of the oxalic acid in these first experimental sets. I want you to recognize that the total volume, by the way, in all of these experiments is 12 milliliters. So you have to use, of course, your C1 V1 equals C2 V2 in order to calculate the concentrations from your original stock solutions. So let's think about the math a little bit. First of all, so I'm using these prime terms in here, so a single prime, and then we have a double prime in here, okay? And so these are two different reactions. So in this particular case, experiment 1 and experiment 2, what's happening here, of course, is the concentration of potassium permanganate is staying constant. Okay, so of course we can always write our rate law. Okay, it's an experimentally determined rate law. So what we can do is we can divide the rate equation for the first experiment by the rate equation for the second experiment. With the concentrations of potassium permanganate being the same, we can effectively write down, there's a single prime term in here in both numerator and denominator because they're the same concentration. They're the same concentration in here. So we can cancel those terms, okay, including the exponent. And now we can simplify this equation. So here's our simplified expression. And we can also now take the exponent outside of the brackets. since it's common to both numerator and denominator. And the next step is to take natural logs of everything in this particular expression. And when we do that, the exponent can come down so that it ends up being a factor for the natural log term on the right hand side of this equation. I personally choose to use natural log ln in my equations, but in this particular case we'll be consistent with the lab handout. But we must note in this case that we're going to use a log of base e in this particular equation. All that's left to do now is solve for y, so simple algebra means that we rearrange the equation so that we have y on the left hand side. We can also recognize that when we go back to our standard rate expression, now if we know what y is, okay, we'd have to also calculate what x is. And we can use a similar approach. If we go back to our original slide, we can see that the difference between experiment number 1 and number 3 is not in the volume of oxalic acid, but we've actually doubled the concentration of the potassium permanganate. We've gone from 1 milliliter to 2 milliliters. And so in that particular case, we keep constant the oxalic acid concentration. So in this particular case, we would cancel this and we could solve for, in the same way, taking logs, we can solve for the value of x, the order with respect to potassium permanganate. I did not mention this earlier, but in fact we can also cancel the rate constant, since it's the rate constant that's the same for both equations. And again, taking natural logs, we can solve for x eventually by doing some simple algebra. So when we know the order of the reaction y with respect to the oxalic acid, and we know the order of the reaction x with respect to the potassium permanganate, we can simply plug in our concentrations for any single experimental set. So let's pick experiment number 1. We plug in that we have 5 milliliters and the concentration associated with that 5 milliliters for the oxalic acid, and we would have a concentration associated with the 1 milliliter of potassium permanganate. Again, both of these concentrations are based on the original stock concentration and are C1V1 equals C2V2. But we plug in the measured rate for that particular experiment, and from that we can solve for the rate constant. The last thing I want to talk about is actually how are we measuring the rate. So what are we doing? We are measuring the loss of this purple color. So where does the purple color come from? Well, it comes from the potassium permanganate. So when the potassium permanganate is used up, the purple color will disappear. So we had to ask ourselves, well, how much potassium permanganate did we start with? And the answer is we have a particular stock concentration. So the stock concentration, and again the final concentration, right? So C1 V1 equals C2 V2. The point here is that potassium permanganate concentration goes from its initial value to 0. That's the change that we're measuring here. That's the change in the concentration that we're measuring. And that change in concentration is happening over a change in time that we measure. But in fact, when we think about it, that change in concentration is simply the initial concentration minus the final concentration, but the final concentration we assume to be 0 because the color purple has disappeared. So in other words, this is our numerator. The denominator is simply the time that we measure on the stopwatch, right? So it's the time that we measure minus our time 0, which is when we started the stopwatch. So we simply end up having a time t that we measure in the denominator of this expression. So we find there's actually some significant errors in this approach. Here's our graph, and on the y-axis we have the concentration of potassium permanganate. So the potassium permanganate decays, the concentration changes over time, so time is on our x-axis. But if you think about it, the initial rate of the reaction is the slope of the curve for the potassium permanganate. But what we actually measure to be the rate, right? We're not measuring an instantaneous rate, we're measuring a rate over all the time of the experiment, of all the time that it takes to take that potassium permanganate concentration to 0, and we're going to find actually that the slope that we measure is our initial potassium permanganate concentration and the total time of the experiment. So the slopes in here are very different. The initial rate is very different to the slope that we would measure averaging over that entire experiment. So these are things to think about. These are things to think about as you consider the experimental inaccuracy, and things to definitely include in your lab report. So thanks for listening. It's a fairly straightforward lab. You're going to work with disposable test tubes. You start your solutions with the oxalic acid in some water, and then you're going to add the potassium permanganate, mix it up very well so that you get that color that takes effect over the entire solution, and then measure the change in that purple color, the loss of that purple color, hopefully against some kind of white background, so that you can easily measure the same change time after time with each of your trials in any given experimental set. So thanks for listening, and good luck with the experiment.